Hello everyone. Now let us continue with the next type of problems on conjugate beam method. So in this problem they've asked to determine the maximum slope and deflection. So obviously it is a simply support beam. So maximum deflection is the center and maximum slope is at the supports. So this is a given problem wherein there are it's a simply support beam and they've asked you uh, to find out slope and deflection. And there are two types of load in this. One is the UDL load and the other is a point load, which is acting at the center. Now when there are two loads as such, so what we'll do is we'll solve the, we'll draw the bending moment diagram separately. So first, as usual, draw the deflected shape of the beam. Then for the bending moment diagram, draw it separately. You see here, this bending moment diagram is for UDL. Again, because things are simple here because it's only one symmetrical. If you cut this across C, UDL is also symmetrical and point load is also acting at the center. So it's a symmetrical beam. So things become simple. And so is AB of span 3.6. So first is we'll draw the bending moment of the UDL only. So bending moment of the UDL is WL square by 8. So it is WL square by 8. When you solve this, it would be 16.2 over EI. So it's like M over EI diagram. Likewise, the next point load. So point load is of 50 kilonewton. Again, it is acting exactly at the center. So bending moment for the point load acting at the center is WL by 4. So again, put the formula. So when you solve this WL by 4, it will be 45 over EI. Okay, so when it is symmetrical like this, so you can directly apply the formula and find out. For UDL, it is WL square by 8, and for point load, it is WL by 4. In case if you don't remember the formula, so the other alternative method is you, as it is, the loads are acting downward. Okay, first find the reaction, use the equilibrium equations and find the reactions. That is summation h is equal to 0, summation v is equal to 0, and moment about a is equal to 0. Then you can find the reactions. So once you find the reactions, you can use this reaction again at C. Just take to the left side, check how many forces are acting to the left, clockwise, anti-clockwise, and you can find out the bending moment. So it's the alternative method. Okay, so now what we'll do is first we'll calculate the total load which is acting downward. Now total load, see, we have split this into a UDL and a point load. Okay, so you have to club this to find the total load which is acting downward. So the load because of the UDL is acting downward and the load because of the point load is also acting downward. So you have to club this. Now to find out this total load which is acting downward is, see again, it's a parabola. So area of a parabola is 2/3 of base into height. So 2/3 of base is 3.6, height is 16.2 over EI. So this is the area of a parabola of a UDL. Next, similarly, area of a triangle, half into base 3.6, height 45 over EI. So 119.88 is the total load because of these two loads which is acting downward. Now to stop this, it will get equally distributed on the left and right. Now because it is symmetrical, that's why directly we'll write this as VA and VB, which gets equally distributed. So 119.88 divided over EI. Again, if you divide this by 2, because this total load which gets split to the left side and to the right side. Total load acting downward should be balanced by total load acting upward. So VA and VB would be same. Okay, so once you draw this, again, it's a simply support beam. So if you draw the conjugate beam, that also would be the same because simply support in real beam is equal to simply support in conjugate beam. So the support doesn't change because simply support remains simply support only. Okay, after this, as usual, we'll find out the maximum slope and deflection. So maximum slope is theta A. So theta A, again, use the formula. Theta A in real beam, theta A in real beam is equal to shear force at A in conjugate beam. Theta A in real beam is equal to shear force at A in conjugate beam. So shear force at A we've already calculated. It is VA. Answer is positive. So it is clockwise. So next, theta b. Theta b would be just the opposite. That means it would have a negative sign. So theta b is minus 59.94 because it is negative. It is anti-clockwise. Okay, next we have to calculate delta c. So delta c is, again use the formula. Delta c in real beam is equal to bending moment at c in conjugate beam. Okay, so come to this point. Now C, at C, we have to refer both the figures. Now again check to the left side of C. To the left side of C, how many loads are acting? Okay, so here, to make things simple, I've shown this two different diagrams. Okay, so VA will remain only one. So VA into perpendicular distance, area of a parabolic curve into its perpendicular distance, that is CG distance, and area of the triangular load into its perpendicular, that is CG distance. Okay, so again you have to see only to the left side. Left side, how many loads are acting? Either, again it is by choice, either you can see to the left or you can see to the right. Both will give the same answer because it is symmetrical. Okay, so let's start with this. So theta c in real beam is equal to bending moment at C in conjugate beam. Okay, so now delta c. Delta c is equal to, okay, check to the left side first. VA into its perpendicular distance. So perpendicular distance is 1.8. So it is 59.94 into 1.8. Now check this out. This is going clockwise. Because it's going clockwise, it is positive. So I've written positive. Next, minus, now see this load, only up to AC point. So this is a parabolic curve. So again, area of a parabola is 2/3, base 1.8, height 16.2. So again, first the area, 2/3 of base into height into CG distance. Again, CG distance of this is, it's measured from C. So from C it is 3/8. From A it is 5/8. So now we, matter of interest is from measuring from C. So from C it is 3/8 times 1.8. 3/8 times 1.8. Okay, next minus this triangular load. Again, triangular load only see to the left side of C. The triangular load is half into base 1.8 and height 45 over EI. So it is half into base into height. Again, you're measuring with respect to C. So with respect to C, if you treat this as triangle, with respect to C, so CAC, this portion, this ordinate becomes base. So from the base, it is 1/3. So it is 1/3 of 1.8. So okay, when you solve this individually, so you'll get delta C. Again, delta C is positive. So positive means deflection is downward. Okay. All right. So in the next problem, it is determine the maximum slope and deflection. Also find slope and deflection at midpoint C. Use conjugate beam method. So here they have asked to find maximum slope and maximum deflection. But in addition to this, there is a point C wherein you have to find the slope and deflection. Okay. So again, in this given problem, AB is a simply support beam, and at C, it is exactly at the center, that is at a distance L/2, and there are no vertical loads acting, but there is only a moment acting at B. So this moment is acting at B. Now it will have a different impact and different bending moment diagram as such. Okay, now to solve this problem, so what we'll do here is, first we'll find the reactions, because reactions play a very important role. The reactions will give us bending moment diagrams, further which we'll find the shear force diagrams. Okay, so there is a clockwise moment acting at B. So first we'll find out the reactions. So we'll use the equilibrium equations. And again, this problem is not symmetrical because there is a clockwise moment which is acting at B. So what this moment does is, you can see here, the arrow itself indicates this arrow when it is shown here. So it will try to push BC upward. Okay, here this portion, if your moment is acting at B, So this, if you try to draw this and imagine, so this load will try to push a BC above like this. Okay, and so first we'll draw the diagram, and then we'll start with the reactions. So we'll start finding the reactions. So as usual, first equilibrium equations: summation h is equal to 0, summation v is equal to 0, and moment about any given point A is 0. Okay, so no horizontal loads. Next is Ra plus Rb is equal to 0. So we don't know Ra and Rb. So we will find out that using the third equation. Now the third equation says we'll find moment about A. So moment about A is nothing but Rb. Okay, Rb, it is going anti-clockwise. So anti-clockwise negative. So Rb into L, total length. Next, moment is going clockwise. So clockwise is positive. So M minus Rb into L is equal to 0. So if you solve this, you'll get Rb. So Rb is M by L. Okay. Next, put this in the equation here. So Ra plus M by L is equal to 0. So Ra, if solve this, then it goes to the other side. So it becomes minus M by L. So one is positive, the other one is negative. See here, we have shown it. Ra is minus M by L. Rb is plus M by L. Okay, so once you find Ra and Rb, then now see here, bending moment at A is 0 because it is a simply support. But bending moment at B would not be 0 because there is a moment acting here. Though it is a simply support, but because the moment is acting here, so bending moment at A is 0 and at B it is M. So written here, P is M. Now because it is a simply support, so there is no changes happening in the conjugate beam. And of course they supported the conjugate beam. Okay, so after this we'll draw the M over EI diagram. Okay, so M over EI diagram. So in this M over EI diagram, at A it is 0 and at B it is maximum, that is M. So because it is M over EI diagram, so I am going to divide this ordinate over EI. Okay, now you can see here, this is RB. If you want to find how much is this ordinate, so what I'll do is, I already know RB. So Rb into its perpendicular distance. Now see here, bending moment. Again, at C, either you can see to the left or to the right. The choice is yours. Okay, so if I check this to right, okay, now see here, Rb is going anti-clockwise. Right side anti-clockwise is positive. So it is M into L into this distance, M by L into L by 2. So M by L into L by 2. So L will cancel, so it is M by 2. Divide over EI because it is M over EI. Now you can see here, I've shown this as negative sign. The reason I've shown this as negative sign is because this moment M will try to push the beam upward. Okay, so moment will try to push the beam upward, and specifically BC portion, it goes upward. Now because it is going upward, so upward movement of the beam causes negative bending moment, which is also called as hogging moment. That's why I've shown this sign as negative. In case if this was acting at this point, say at A, it was acting like this clockwise, that was tried, then it would have tried to push AC downward. So when it pushes downward, then it becomes sagging bending moment or positive bending moment. Now because this moment is it is trying to push BC upward, so that's why it becomes negative. So I've shown you a negative side. All right, so once you draw this diagram, the next thing is we are going to find the VA and VB. Now check this out. So because it is not symmetrical, so all the problems we have solved previously were symmetrical. So whatever total load would be acting, we would divide it equally on A and B. But now here at A it is 0 and linearly it is varying, and at B it is maximum, that is M over A. So for such type of problem, what we'll do is we'll find we'll again use the equilibrium equations to find out the shear force. Like how we have found out reactions here, the same method will be used to find out the shear force here. As here, it goes like this. So again, use this diagram. So in this diagram, we have to find VA and VB. Now to find out this V and VB, there's basically shear force. So we'll use first, that is VA plus VB. VA plus VB is acting upward. Then this triangular load is acting downward. Okay, so we'll use the equilibrium equation, that is find moment about A. So moment about A at this point. Okay, let's start with this. So VB is going anti-clockwise. So anti-clockwise is minus VB into L. Okay, then this triangular load. Now see here, this triangular load is acting downward. So this triangular load will take this complete. Now see here, we'll not split this into two. Though we have written here m by 2 here. So to make things simple, because it is from A to B, we'll write it directly. It is half into base L, height m over EI. Okay. So then because we are measuring with respect to A, so from A to this point, CG, again CG of the triangle measured from the apex is 2/3 of L. So it is 2/3 of L. So when you solve this, you get VB is equal to ML over 3EI. Okay. So once you find out VB, next is we'll find out VA. So we know that VA plus VB are the reactions upwards, and this triangle load is acting downward. So VA plus VB is equal to total load. So now let's see what is the total load. So total load of this is half into base L, height m over EI. So half into base into height. So it is, when you solve this, it is ML by 2EI. This is the total load acting downward. So you put it back in the equation here. So VA, we already calculated VB. So substitute this VB here and solve this. So you'll get VA is equal to ML by 6EI. So VA is ML by 6EI, VB is ML by 3EI. Okay, now this VA is having a lesser value compared to VB. Again, the reason because the moment is acting exactly at B. So it requires more shear force to stop that. So that's why VB is more. Okay, so once you find out V and VB, next is simple. Again, we'll use the formula, that is first we'll have to calculate maximum slope and maximum deflection. So maximum slope would be at A. Okay, so theta A in real beam is equal to shear force at A in conjugate beam. So theta A would be VA. So VA is ML by 6EI. Similarly, theta B. Now theta B is VB. Okay, here it is different, not like the previous one. So VB. So VB is also positive, which is ML by 3EI. VB. Okay. All right. So theta max would be at B, that is ML by 3EI. Similarly, let's calculate the slope at C. Okay. Okay, let's calculate the slope at C. In bending moment. Okay. Bending moment at C in real beam is equal to same. Bending moment at C in real beam. Find out shear force, or the first find out the, we've already calculated the bending moment here. Okay, so again, no need to write this. So directly we can start calculating the slope and deflection at C. Theta C in real beam is equal to shear force at C in conjugate beam. Theta C in real beam is equal to shear force at C in conjugate beam. Now see here, so we are talking about this. So again, to the left side of C, just check to the left side of C, how many forces are acting. Okay, so there is VA and this area of this triangle and VA. So to the left side of C, so if you're finding only shear force, means you have to only consider the forces. So VA is equal to ML by 6EI, which is acting upward, positive. Then downward is only this triangle load, that is half into base L by 2 into height M by 2 EI. Okay, so it is ML by 6 EI upward. Then area of this triangle load downward, half into L by 2 into M by 2 EI. So when you solve this, you'll get theta C. So once you find theta C, next delta C. Again, delta C is delta C in real beam is equal to bending moment at C in conjugate beam. So delta C in real beam is equal to bending moment at C in conjugate beam. Okay, so bending moment at C would be, again, see to the left side. So to the left side, again, there are two loads, VA into perpendicular distance and this triangular load into its CG distance that is measured from C. Okay, so VA into its perpendicular distance. Perpendicular distance is L by 2. So ML over 6 EI into L by 2. You can see here ML over 6 EI, ML over 6 EI into L by 2. Now again it is going clockwise, so it is positive. Then minus this triangle, half into base L by 2, height M by 2 EI is this area. Same thing here. Half into base into height. And now you're measuring with respect to C. So with respect to C, again, centroid of a triangle measured from the base of the triangle is 1/3. So this is 1/3 of L by 2. So that's why it is 1/3 of L by 2. So when you solve this, you'll get delta C. So delta C is equal to ml square over 16 EI. Okay, that's it for today. Thank you.